guys, this is a relatively short introduction into some characteristics of solids, liquids, and gases. And we want to consider it a little bit in particulate characters, and kind of see what we're doing. And then we're going to do a really fast review of each of the individual gas laws, because we'll be able to really put it together when we do the combined gas law in the next unit, as well as the ideal gas law. So let's start with solids. You already know about solids from a, kind of chemical characteristic, but understand that in a solid, the motion of the particles is very limited. Most of the motion is vibrational. So make a note of that. All right. And some rotation may be possible, but really most of the motion is vibrational. The next slide talks about amorphous solids. Amorphous solids are like gas and stuff like that. And they have a random arrangement of particles, and you can kind of read about that. But examples of amorphous solids are glass and rubber. Crystalline solids, ionic compounds are a great example of crystalline solids. And as you know, they cleave along planes because the ions are arranged in a structure that repeats itself in all three dimensions. Now, metals usually don't cleave along planes, even though their atoms are arranged, and that's because in metals, as you know, the electrons move around from atom to atom in a sea of electrons. And then the next slide looks at amorphous and crystalline solids. And the pictures really just, understand that glass is amorphous and quartz is crystalline. And think about the ability to break each of them, okay? It's kind of easy to break glass. And if you look at the structure, you can probably, see why. Where quartz is usually a lot more sturdy, kind of. All right, properties of liquids. The biggest thing to take from this is that in liquids, the particles are moving more than they are in solids. The intermolecular forces are weaker than they were in the solid state. And so the movement of those particles is really influenced by the strength of the intermolecular forces that are present. And the particles are still kind of close together, but not as close together as they were in the solid. And so what we're going to think about here a little bit with liquids is temperature. And you can hear my pen. And hopefully you remember that temperature is a measure of the average kinetic energy of the particles. And kinetic energy is equal to 1/2 mv squared. Not that you have to calculate that, but understand that temperature is a measure of the average kinetic energy or the movement of the particles. And so the faster or the more that the particles move, the higher the temperature. So particles are moving faster at higher temperatures. So solid and liquid phases generally have small differences in molar volume. The particles are really pretty close together in both. Most solids, except for ice, and that's because water is such a polar molecule, but most solids have a slightly smaller molar volume. You don't really have to take anything away from that. All right. So as you can see, here we have approximately the same number of particles in the same area. So we would not expect the density of the molecules to change very much. So in this example, the density of the particles in the liquid phase here is slightly less than the solid phase. But a volume usually increases as density increases. So you may want to make a note of that. Okay? All right, pressure. This is the basic formula for pressure. You don't need to memorize it, but it will give you an idea of what pressure actually is. It's a force being applied over a certain area. In this equation, the units for pressure is pascals. In this course, we're also going to use atmospheres, and we will also use millimeters of mercury for pressure. So basically, gases exert pressure. Gas particles bounce off surfaces, they create a force. Since gases are pretty evenly distributed throughout a container, the same number of particles smash against every square centimeter of that container every second. Thus, the same pressure is being applied to all surfaces of the container. So pressure equals force divided by area. Here you are, okay? So the same thing's happening to you. Yay, look how happy you are. You have about 1 atmosphere of pressure on every square centimeter of your body as you sit and listen to this lecture. Basically, it's caused by the gas molecules in the air bouncing off of you. You don't feel it because the liquids in your body push back with the same pressure. So 1 atmosphere is the average atmospheric pressure at sea level. It varies somewhat due to the weather. So if you feel like it, you can look up the current atmospheric pressure and see what forces are pushing back from your body. Here we are, we're trying to suck gas particles out of a can. So in the first picture right here, the pressure inside the can equals the pressure outside the can. The vacuum's off. The rate of collisions inside the can equals the rate of collisions outside the can. But if you create a vacuum, right, our vacuum pump is on, by sucking the gas molecules out of the can's going to implode. And this is going to happen because the pressure inside is less than the pressure outside. And the pressure difference is caused by the fact that there's fewer, right? There's 1, 2, 3, 4. There's only 4 in this example. Gas molecules colliding with the inside surface of the can than there are with all of these guys outside the can. And the greater pressure caused by the greater number of collisions on the outside of the can crashes the can. So it's a way, when you come to class, remind me to show you how we can crush the can. Okay. Barometers are the tool that's used to measure gas pressure. So the atmospheric pressure pushes the mercury in the tube, basically. So we have mercury in the tube, and the atmospheric pressure is going to push the mercury up the tube. And it's pushed up by the atmospheric pressure pushing down on the mercury in the pan. So there's no pressure inside this tube. But if you place a tube in mercury that is open at the top, like let's say we didn't have it closed, here we're closed at the top. If you had it open at the top, the mercury wouldn't rise because the pressure from the atmosphere would be the same inside and outside the tube. So this conversion here is one that you will need to use in the course. And we'll check your reference sheet to see if that's on there. But 1 atmosphere is equal to 760 millimeters of mercury, or 760 torr. So let's review the gas laws, okay? Boyle's law looks at the relationship between the pressure and the volume of gas, and this law is going to be true when the temperature and the number of moles, I'm going to call that N, the temperature and the number of moles of gas remain the same. If you take a gaseous system and decrease the volume by half, the pressure will double it. Now I'm going to cut to the chase right now and tell you if you can remember that P1V1 over T1 is equal to P2 V2 over T2, or the combined gas law, you can remember all of these gas laws. You'll notice here is our Boyle's law, right? Volume is inversely proportional to pressure. So looking at the pressure-volume relationship, Boyle's law is going to be true. We're going to keep the temperature constant. Temperature is a measure of the average kinetic energy. Kinetic energy can be either rotational, translational, or vibrational. But to make this a little simpler, we're going to say that it is directly proportional to the translational part of the speed. Now, just kind of visualize it. If we decrease the pressure, right, the same number of molecules are now occupying half the space. And so they're all moving at the same speed, but you'll get twice as many collisions, and that's going to cause, in a smaller amount of space, and so that's going to cause the pressure to double. So hopefully visually you can kind of see that. Let's take a look at temperature. Remember again, temperature is a measure of average kinetic energy of the system. We're going to look in chemistry at Kelvin temperature. You'll remember Kelvin is equal to degrees Celsius plus, does anybody remember? Yes, 273, okay? And so when the kinetic energy doubles, the temperature, the Kelvin temperature, is going to double. Kinetic energy of gas molecules basically move in straight lines until they bounce off of something. They can also rotate, and they can also vibrate. But most of the gas particle's kinetic energy is equal to its translational velocity. So let's take a look at Charles' law. Again, I'm going to combine them for you. P1 V1 over T1 is equal to P2 V2 over T2. All right, now we're looking at the V1 over T1 equals V2 over T2. This is a proportional relationship. That means when one goes up, the other goes up. When one goes down, the other goes down. The very important part of that is that you have to use Kelvin temperature to make these calculations. Why does this happen? Okay, temperature is a measure of the average kinetic energy. So if the temperature is reduced, the particles will now move slower, okay? So what that's going to mean that on the average, the gas particles are going to collide with one another and the sides of the container more slowly if you reduce the temperature. And that allows them to maintain the same pressure within the confines of half the temperature. We're keeping the pressure constant, and we're only changing the temperature and looking what happens to the volume, or the volume, and looking at what happens to the temperature. So there will be twice as many collisions taking place per square centimeter, but each collision will have half the kinetic energy. So the pressure is going to be the same. But hot air rises basically because it's less dense. So properties of gases, the particles are constantly moving. They have lots of space, okay? They expand to fill the volume of the container that they occupy. Their density is relatively low. They're highly compressible, and they exert a pressure. Gases do not have a definite shape or definite volume, but they're considered to take the shape of their container. But they collide frequently, and the density of the gas particles is going to depend on the pressure, the volume, and the temperature. And so in future lectures, we're going to put all of that together. Here, you have a diagram of the solid phase, the liquid phase, and the gas phase. So what I want you to notice here, notice the dashed lines. Remember, what do those represent? Ah, yes, that's right, the intermolecular forces. So, what do you notice missing from the gas phase? That's why it takes so much energy then to go from the liquid phase to the gas phase, because we're trying to overcome all of those intermolecular forces. And this diagram's even limiting because the particles would be much further apart from this in the gas phase. Ideally, there are no intermolecular forces between the particles in the gas phase. So, armed with these notes, I want you to go forth and do the 3.1 to 3.3 concept check in AP Classroom. As always, feel free to contact me with any questions. I look forward to seeing you guys. Thanks.